So I've started recording this. It says recording, cool. So I was back to screen share and open up my thing here. So we've opened up our blank simulation. I'll start it again, I guess, from the top. So we choose just blank simulation, create, and it's gonna wanna know if I wanna keep this. So I don't wanna keep it, so I'm gonna say yes to close, don't save it. So we have a new blank simulation. So first thing we're gonna do is we're gonna add water and NaCl. Those are our two main species we'll be using during this. However, here's the trick. Do you remember when he used the electrolyte wizard, how we set up like two different sodium chloride species? We had one that it was this conventional and one that was mixed. Well, the trick we can do here is where it says conventional, if we change that to solid, it makes our lives a lot easier down the road. Then what I'm going to add is Na plus and Cl minus. Because I know in the system, sodium ions are going to form and chloride ions are going to form. Continuing, so we're going to hit the electrolyte wizard. We don't change anything here. We're going to move everything over. We're going to leave everything else as is. Hit next. And we see here that we have one reaction that's introduced for us. So we have this back and forth salt reaction. So sodium chloride, solid, it can dissociate into chloride ions and sodium ions. We want to leave everything else as is. Next. True component approach. Next. And then just finish. So you see nothing's been added here, right? The real advantage of using the electrolyte wizard is this. So under chemistry, this is just, we're not inputting anything, I'm just to show you. Under global input, you can see that there's this reaction here, this salt reaction. And I'm not sure if I can actually see chat. Okay, cool, I can now. You can see that we have this salt reaction here. And the power of this electrolyte wizard is that under equilibrium constants, it actually pulls this information for us. Whereas before it wouldn't. Before we'd have to enter that manually. Okay. So we only have one more thing to do here. We have to go under methods, parameters, and we just have to click these two. Electrolyte wizard pulled all this for us. So we just need to check them by just clicking on them. We hit next. Run property analysis setup. It's getting all our information from databanks, and we're done. So now we're ready to start with the actual simulation setup. So we're setting up our flow chart. Let me see if I can pull something here. Okay.
He says hold up.
Oh, sorry. Oh, sorry. Lost me at parameters. Oh, so let me go back. Properties. So under parameters, all we have to do, you'll see they're going to be red circles here. We just have to click here, then click here. We're doing nothing other than just looking at them. It's a formality Aspen has us do because it needs to load these parameters by opening the folders. The electrolyte wizard actually generated all these for us, but Aspen just wants us to make sure we load them. So that's why we have to click on binary interaction, then electrolyte pair. So we're not inputting anything. We're just checking them basically and loading them. And when I was showing this chemistry thing, that was just me showing you that that's what electrolyte wizard does, but we don't actually have to do anything with that. It's all automated. So from the top, the only thing we have to do is go into specifications, put in our species, electrolyte wizard, continue through the electrolyte wizard, click on binary interaction, and electrolyte pair, and then we're ready to go. So now we can actually proceed to simulation. Now, a key thing before we do anything in this whole simulation is change something called a stream class. What a stream class is Aspen can separate flow, like material flows, into something called a subclass or a substream. What a substream is yes, we may have, let's say this stream here. This stream can contain lots of things. Like we could have ammonia in there. We could have carbon dioxide. We could have it in, we've only ever really dealt with so far liquid or gas forms. We did things where we had a flash drum, still only in liquid and gas, but we've never really dealt with solids until now. Well, Aspen actually has a special, it's called a substream that handles solids. So to set this up, we go under Setup, Specifications, and under Global Settings here, it says Stream Class. Currently, we're at Conventional, meaning standard, like nothing, we're not changing anything. In order to have solids, we need to change Conven to MIXCISLD. This stands for Mix Conventional Inert Solids. So it means we'll have two substreams, a substream called mixed and one called conventional inert solid, which I call CI solid. And that's all we really have to do for this part. So we go back to our flow sheet here, the little tab section here, flow sheet. We're going to add, we already have our input stream, which I will name feed. We go under solids, because that's where all our solid stuff is. So we see things like the crystallizer, crushers. In Aspen, you can actually model size of particles, and that is handled by these some of these operators here. We're only dealing with crystallizer, which deals with solubility. So I'm just going to put that anywhere. I'm going to right click on my stream.
Wait, why didn't you use the other one?
Which one?
When you click on crystallizer.
Oh, you mean I don't use this one here?
That one, yeah.
Oh, they're all the same. They're just different images for the same thing. So all of these,
really?
yeah, all these here, they're just different like icons for the exact same process, right? It's more for a visual aid. So if this is usually for something, if we have like a reflux, we don't have a reflux, right? But they both can. This can also have reflux. They all function the exact same. So I could have this here instead, and it will function the exact same. This is completely just a visual element.
Oh, okay, I see. Wait, how did you delete that?
So I just clicked, I highlighted the area around it, and I just pressed delete on my keyboard.
Oh,
it says delete block. So we're here. Now, initially what you could have done is went to material and then drew an arrow from here, but I already have this arrow here. I don't really want to delete it. So I can right click the arrow, reconnect, destination. So when I click here now, you'll see that it kept the stream, but then it actually connected it to this crystallizer. So we have an input stream. We're going to add an output stream. And remembering that blue streams are optional, red streams are required. So we already have an input here, so it turned blue. We don't have an output here, so it's still red. So I'm going to just put that there. Doesn't matter which direction it goes, up or down. It just visually. I'm going to call this brine, which is a technical term for a saturated salt solution. Oh, yeah, I can wait. Really? Oh, did you do the reconnect thing?
Click on the left side and then connect it to the arrow. It should be a red arrow on the left side.
Another thing you can do, let's say I didn't have this stream, if you hadn't made one beforehand. So you go under material, click your material stream, just click on this red arrow and then drag that away. That does the same thing. So I'm going to rename this feed again. So this is our entire flow sheet, right? In terms of the amount of things we'll have on here, this is all there is. First thing I want to note is we're going to go under feed. So you can either right click feed and go input, or if you double click the stream, it'll open up automatically the input section for that stream. So if you look here, we're actually under streams, feed, and we are in the input section here. So normally in a normal stream, if we didn't change that stream class thing that we did at the beginning, it'll just say mixed. But we actually see now that we have this CI solid, this conventional inert solid. This is where we're going to handle solid materials, like the solid salt. So you can see in the mix, we can do anything here. And we could have any material in this flow. You'll see in the CI solid, that's not the case. We only can have solids in this case. So we're going to go to the mix first. So in the homework file, it said it wanted us to flow 20C, 1 ATM. So 20C. And I'm going to change this to atmosphere, 1 ATM. Now, in class, he's been doing a lot of stuff with this total flow rate section. Completely ignore it. Just don't deal with this at all. This whole total flow rate section, I find it overcomplicates everything and it makes it a lot more confusing. Really, only ever deal with composition, this composition section. So, under composition, we want a mass flow of water. That's the problem calls for 100 grams per second of water. So under mass flow. So you can see our units changed. So we're going to change it to the unit of grams per second, and Aspen denotes grams as GM. We're going to say we're flowing 100 grams per second. And we see actually all of this turn blue. All of it is required input for this part is complete. Because technically we don't need to have anything in the solid stream. But we do want something in the solid stream. So we're actually going to go over to CI solids. This is where we're going to set up the salt input. Under temperature, the same conditions as before. Because Aspen can handle these streams with different conditions somehow. Physically, it wouldn't work, right? So I'm saying that if you look here between mixed and CI solid, same conditions. So under mass flow, we want mass flow again for grams per second, as the homework states. He wanted 100 grams of solid sodium chloride input into the system. 100. And this stream is completely defined. We have some in the mixed. We have some in the solid. You'll see how we did not put a total flow rate here. That's completely okay, because our total flow rate is determined by what makes it up. So we say composition, 100 grams per second. Total, 100 grams per second. What he is doing, essentially, let me put this in a hypothetical tense, okay? Let's say somehow we managed to flow 100 grams per second of sodium ions, right? Can't really do that, but let's say somehow we managed to flow 100 grams of sodium ions. The total mass flow of this system will be 200 grams per second. We've added just another 100 grams per second. However, if we specify over here a total flow basis of like 2,000, and this is completely hypothetical, guys, this isn't part of homework. If we say 2,000 kilograms per hour, it's still all blue check mark. But what this will now interpret this as is it's a 1-to-1 ratio of this total flow rate. It's kind of confusing, I find, but this is how Aspen handles it. Because if you specify total flow rate and composition like this, it'll take this as the total flow rate, and it'll use these numbers as a composition. So let's say I had, instead of 100 here, I had 50. What this will now say is, this is a 2-to-1 proportion of this 2,000 kilograms per hour. And this confusion is why I don't really like using total flow rate. So I usually leave it blank. You'll see how it went unbold. I prefer to leave it as is. This will work, in my opinion, better. So for our flow, our streams are completely set up now. Now the last thing we have to do is set up the crystallizer, which I'm going to rename Crystal. You don't have to rename anything in Aspen, but I find it just keeps track of what's what a little better. So doing the same thing, either right-clicking and clicking input or double-clicking on the crystallizer will bring you to the input section. And this is where a lot of people have been getting tripped up, because they see specifications crystallization and solubility. And they see a lot of like this reactance section, and they see the solubility section. They get confused. Well, actually, we don't have to do anything with these. So in our homework, it's still specified that it was 20C, 1 atm operating conditions. Scroll up. And the next thing we have to do is click chemistry. If you'll remember earlier on under properties, we went into that chemistry section so I could show you where the equilibrium constants were. What this does, this saturation calculating method being selected as chemistry, is it will pull equilibrium data from the salt we select here to be used for solubility, rather than having to manually input it ourselves. So under salt component ID, we tell now the crystallizer we're dealing with sodium chloride. We have one more thing to do. Under crystallizing, under operating mode, we want to change this to either. Because if you do anything that isn't either, it'll throw up errors with you, and it can only do one operation. So if you had dissolving or melting, yeah, it could dissolve or melt sodium chloride, but what if it's possibly not just dissolving, or what if it's not just crystallizing? What if it could be either? That's where this either comes into handy, where it can do anything. It will just do a general solubility reaction. So if we see at the bottom left here, it says required input complete. We are actually completely ready to run our flow sheet. So if we go to home, click run. It's going to think for a second. And we see that everything here kind of turned this nice light blue. That means we have good data. So if we go under here at the bottom, results summary, streams. This gives us all the streams in our entire flow chart. It'll give us the data of streams. So here we have streams. We have brine and then feed. I'm going to switch these around, so it goes from input to output. It does nothing other than make it easier for me to visualize what's happening. So we have to, under total stream, we're going to go mass flows. And we'll see there in equals out. That's good. I'm going to open this up so we can see what we put in, and we can see what we're getting out. However, this is in kilograms per hour. Remember, we put things in as grams per second. So we want to see in a unit that we were already operating in. We want to see what's the reaction happening. So we see here, water, 100 grams per second in, sodium chloride, 100 grams per second in. You will notice there is less solid sodium chloride coming out of the system because it was dissolved. This is the operation of the crystallizer. This is the point of the crystallizer, is the fact that it is able to do this solubility reaction. Given an amount of water, given an amount of sodium chloride, a certain amount of ions will be generated. To calculate the solubility of sodium chloride at this temperature and pressure, right, with water, all you would have to do is take the sodium in minus the sodium out. So in this case, I think it was 35.8 grams of sodium chloride per 100 milliliters of water, or 100 grams of water. Because remember, water has been defined as 1 milliliter is a gram. And that's all there is to it. We actually have our solubility data. The entire homework is now done. But I want to show you something. You'll see here where it says mixed substream, and it says CI solid substream. This is where we're going to, this is where Aspen handles those substream things I was talking about. So if we go under mixed substream, and notice how we were just dealing, originally, we were dealing in total stream, so the composition of the entire stream. Let's just look at just mixed substream. So under mixed substream, mass flows, we're going to change it to gram per second. We're going to open that up. And we'll see here that no sodium chloride was in the mixed stream in the input. And there's also still none in the output, because we told the system not to handle solids in the mixed stream. But you will notice that there are ions now in the mixed stream. And in this case, you'd think, oh, hold on, in doesn't equal out. But remember, this is just a subset of the total stream. If we go down farther, we will see the CI solids substream. This is just where solid stuff is handled. And this might be a little more clear for figuring out solubility, the substream. Same thing, mass flows, gram per second. Open it up. We can see that some of the information we saw before, where we put in an amount of sodium chloride and we got out less. Because an amount of it was turned into, as we can see, this difference is equal to the sum of these two ions. So the amount of mass that was transferred into the mixed substream is equal to the amount of mass taken out of the CI solid substream. And because these are both substreams of the exact same total stream, if we look at total stream mass flow, in equals out. So Aspen just handles those two substreams differently. And remember, CI solids is specifically for solids. Mixed handles things like liquids or vapors. And that's really it. But let's just for an example, and this is the homework. The homework is now done. This is all the information you'll need for the homework. Let's say, what would happen if we were to feed less water? How about 75 grams of water? Well, okay, we just hit run. Now that we've changed we've only changed something, but everything is still defined. We can go back to our results summary. And we will see we'll have more solid sodium coming out. Okay, and you'll see it changed it again. So our mass flows have to be changed into gram per second. 175 in, 175 out. But there is much more of the sodium chloride coming out. That's still solid compared to last time where we only had about 64 grams coming out. Now we have 73 because there is less solvent here to dissolve the solute NaCl. Meaning there's less stuff that will become dissolved and more solid stuff will be left in the outflow stream. And so for part of the homework, they ask, how would you, what operation would you change for this crystallizer, this here, to produce more solid sodium chloride? And really, the only thing you can do is give it less water. Because, and I checked this using some analysis tools, there is no pressure or temperature where you get more than like the 10% he wanted. In the homework, he asked for 10% more solid sodium chloride. There are no pairs of temperature and pressure that will produce that much sodium chloride. And I can show you that if you'd like, but really the only thing we can do is this feed, is change the amount of water in the feed. So I'm gonna put it back to 100. Run again. Back to our results summary. Change our units. Gram per second. And we're back to where we were. And this is the homework. This is all you need to do in Aspen, is this part here, is just get this information. They're gonna ask the component flows of each component in the input and the output. And this is where you'll get all that information here.
Okay, so I have a question about that.
What's up?
So for that part of the homework, we also changed it to kilograms per second too.
Yeah.
Right, okay.
Yeah. All he wanted in this is in the flow sheet, he wanted you to feed 100 grams per second. But yeah, you're right. In your summary sheet, if you didn't want, this, you could then change it to, was it kilograms per second?
Well, I added both.
Okay, that works. Yeah, because you could do either way. He just wanted in the input, that's how much he wanted. But you could do anything after that.
Okay.
Yeah, that's really
And then as far as if we wanted to produce more solid, then that means that there's less dissolved salt, right?
Exactly. And that means there would be more solid sodium chloride in this stream because less would become ionic. And so that's what I was talking about. Feeding less water is really the only option we can do because, and I can show you. Let's go into properties.
Oh, so it's feeding less water, not lowering the temperature.
Yeah, and I'll show you why the temperature doesn't really help it. So do you remember how the other day we were in properties and we were going over binary stuff with water and ethanol? You kind of rushed through it, but the main point was you can actually use Aspen to generate really useful charts and tables. One of them we can use is solubility. And for this case, it works really well. So we're going to say our solute, what's being dissolved, is sodium chloride. Our solvent is water. And we want this in a basis of mass. This actually doesn't have any effect on it, this whole kilogram per hour thing. It's just mass that we need to worry about. Change the mass. All right?
Okay.
So under, okay, what else do we need here? Points. I'm going to change our starting point from 5 to 100 in increments of 5 degrees C. And for water, you just need to put 1 here, just to show that it's just water. The fraction is 1. And we can actually run the analysis here, and it will generate a really nice graph for us. This is measured, by the way, in either kilograms per liter or grams per milliliter, the unit conversion. This is what this is. We were operating at 20 C, right? You see the bottom here, it's in Celsius, which is here. And that's exactly what we had for an answer. It was 0.358. If we go back to our simulation, we'd see this was the solubility that Aspen found and used. Now, I want to know what would happen if we change pressure, because we can see that we're kind of at the bottom here. In fact, there's only about 5 degrees that'll change anything. But if you look at the scale here, we're not getting an extra 10% out. We need at least 3.5 grams extra precipitated salt, right? We can't get that with any temperature here. But this is at 1 ATM or 1.0132 bar. Well, let's see if we can get any pressure that will give that to us. So I'm going to change it to ATM, so it's a little easier for me to read. ATM, I'll change it to 1. And I found, personally, the highest pressure that Aspen lets me input in this is 1 e to the 4th. 10,000 ATM. Right? So under this parametric variable, what it means is it will generate a 1 curve for each of these. So it'll generate a solubility curve for 1 ATM and a solubility curve for 10,000 ATM. So if we hit run analysis again, it'll bring us back to our graph, and we'll see these 2 sets of lines here. This here is at ambient temperature, well, ambient pressure, so 1 ATM. This is at, ocean depth pressure. And we can still see that not a lot more precipitated out. Maybe a fraction of a gram, not what we need. So the only thing we can do is feed less water. Or, alternatively, there is an alternate to this. If you remember back to your equilibrium chemistry, you actually could feed something that involved a chloride ion. But that's a little more chemically inclined than we need. Really, the best situation we could do is just feed less water.
So feeding less water into the stream will cause, what will that cause?
So less water means that less solid sodium chloride will be able to be dissolved.
Just because of that ratio.
Yeah, it's just because, simply put, there's not enough water to dissolve all the sodium chloride. So
Okay.
if we put more water, let's say we put some sort of crazy amount of water. Let's say we put 1 kilogram per second of water, 100 kilograms per second. So I'm just changing the unit, right? Nothing else has changed except for that 1 unit. If we hit run and we look back at our results, assuming I'm going to find this answer, doesn't even matter the units, we see that there is no solid sodium chloride coming out of this. It's all turned into ionic species because sufficient water was input into the system to dissolve all the sodium chloride.
Okay, I see. So, for specifically for this simulation, it's not reasonable it's not a reasonable system because there's still solids in the simulation.
Yeah.
And ideally we want everything to be dissolved, and we don't want them to be left as ions, because then that can cause problems as far as like it being stuck somewhere and building debris.
Really the point of this simulation is just for us to get comfortable with feeds and solids feeds. There's not necessarily an objective we're trying to reach here. Really the biggest thing we wanted to get out of this simulation was this stream information here. Because based off of this, yeah, that's really it. And so, I mean, yeah, you could make an argument. Let's say your objective in this in the system, if you were to do something in real life, let's say your objective was to dissolve all of the sodium chloride, right? Yeah, you're right. We would need more water because currently we have quite a bit left over. And that if our goal was to dissolve it all, we're not achieving that goal.
Well, the reason why I mention it is because in one of the questions on the homework, it asked if Aspen does a, let's see.
I think it was like a good job, if you think this is a good simulation of the system.
Yeah, and I put, something about the feed stream specification, and if we think it was reasonable. And I said no, because not all of the salt was being crystallized, and there were still a lot of ions that were being remained.
Well,
so just,
on the contrary to that, actually, so think of like normal solid salt, right? Let's say you had a glass of water and you had a bunch of table salt, and you kept pouring table salt until no more table salt is dissolving into it. That's essentially what this is just that system. So in reality, if you do this, in actual life, you fed 100 grams per second of water, 100 grams per second of sodium chloride, this actually probably is what you get for your output, for your brine. This is probably pretty close to what you realistically reach. So it's not that in real life, salt doesn't completely dissolve. If we have enough water, it will completely dissolve. But quite often, in cases like this, we will find that as much as possible dissolved until it reached its saturation point, and then the rest couldn't do anything. So we really could do this. Yeah, we could do the same thing with any sort of salt. So not just table salt, sodium chloride. We could do it with silver nitrate. We could do it with calcium nitrate. We get all sorts of different calcium chloride, magnesium chloride, all these different salts. They all have specific properties that are inherent to the salt themselves that would dictate how much does dissolve into this.
So then I should change my answer that it is a reasonable simulation.
Yes, I would say this is, I would give it a 9 out of 10. And the only reason I don't give it a 10 out of 10 is because it bases its solubility per temperature and pressure based on a fitted curve, which is, again, Perry's Chemical Engineering Handbook tells us that the solubility of sodium chloride in water at 20 C1 ATM is 36.0 grams per 100 milliliters of water. This is telling us 35.8, right? So that 0.2 is a little off because of the fitting, but in reality, in practice, that's such a small difference that it would never become a problem for us.
Okay, cool.
And another thing,
you so much.
Another thing I will say, so do you remember how he did this, the sensitivity thing in lecture?
Yes.
Okay, I can show you really quickly how to do a really neat sensitivity thing. So let's say our objective for this was to dissolve all of the salt without using a bunch of extra water. You don't want to waste water. Let's say we want to dissolve all the salt but without using a ton of waste. So it's actually a really cool way to do that. So I'm just closing all my things. So under model analysis tools, there's a couple different things here, and all these things are different things. So optimization is like is something for if you want to maximize profit or maximize the amount of a certain product in a stream. Sensitivity is just saying change one variable, plot a point. Change another variable, plot a point. Change another variable, plot a point, one at a time, and gets you a nice table that says, okay, if I feed my water at this rate, the output salt will be this. How about this rate? How about this rate? And you can specify that. So it's actually not as bad as he showed in class. So you click sensitivity and you just click new. This means we're doing a new sensitivity study, just called S1 by default. That's a fine ID. So it's going to bring us into this. So under the vary tab, vary means this is the variable that we are actually going to change. This is our independent variable. We're inputting something into the system and we'll get out whatever number we want down the road. So for vary, let's say we want to change how much water goes in the system, right? We want to see the impact of the amount of sodium salt out versus this water we put in. So we're going to say new, a new variable to be manipulated. And for type, we're going to go mass flow. So we're going to change some sort of mass flow. And this variable number doesn't mean anything. Just ignore that. We're going to do some sort of mass flow. We want to change the amount of water being put into the system. So we're going to go feed. Remember that water is liquid, so it will be handled in the mixed stream. CI solid is specifically for sodium chloride, but in the mixed stream, it'll be here. And for the component we want to change, we obviously want to change water. And we're going to say, we're going to change it in units of grams per second, because that's what we were dealing with originally. So now we want to see how many points do we want to plot. I want to say between 5 grams per second and 305, right? Arbitrary numbers. But this arbitrary number allows me to do this. In increments, you can do points or increments, right? Of 10 grams per second. What this means is we will get a table with the first point being 5 grams per second of water, 15 grams per second, 25, 35, 45, all the way up to 305. There will be 31 points plotted on our table. That is this tab done. Now we have to go to define what variable we want out. We have our independent. Now we have to define our dependent. So we click new. Now I will, you know what, I'm gonna, actually, there's a better way to do that. If I go streams, click new here. I'm gonna call this salt out. The name is irrelevant. It's just for reference to know that what are you looking at? What number are you looking at? I'm gonna say salt out. So now we're gonna go to streams. I guess it unselected it. Go under streams, reference type, and we want another mass flow. We want to see how much salt is leaving the system in solid form. So mass flow. The stream was our brine, so our output. Remembering that solids are only ever handled in the CI solid substream. And we want to have sodium chloride, the only solid we have in the system. Again, we want it in units of grams per second. All right, that is this one done. Tabulate, all you have to do in tabulate is just click fill variables. So in the output table, it just means that for column number 1, this is what you want there. And this is automatic. Whenever you hit fill variables, it'll say, do you want to remove existing ones? And you say, sure. And it'll just replace them with whatever you have defined in the define section. So our sensitivity study is done. Now we have to hit run. So, and we'll see that we have this blue box here. If we click on results, we actually have all of this data now. And it doesn't change it to grams per second for some reason here. But just know this is in kilograms per hour. This is in grams per second. I'm not really sure why I've been having problems with the unit here. But just know that this is an increasing amount of water as we go along, as we can see. This is 5 grams, 15, 25, and such. This is the salt out. And it makes sense because if we put 100 grams per second of salt in and 5 grams per second of water in, only a little bit of salt will be dissolved. So it's just a little bit under 100. As we increase the amount of water, we see that the amount of salt that leaves the system is decreasing because more is being dissolved. This trend continues until we see all of the salt is able to be dissolved. So if in our system, our goal was to dissolve all of the salt without wasting any water, we would pick a water flow between 990 and 1026 kilograms per hour of water. I think that would be 305, 295, 285, between 275 and 285 grams per second of water. That's the power of the sensitivity, is it lets us tabulate what if values. What if I put this much in? Well, this is how much you get out. What if I put this much in? This is how much you'd get out. And you can have lots of different columns here. Let's say you wanted to know how much sodium ions are also leaving. You could do the exact same thing. How much chloride ions, how much any part of your system, you could also tabulate it. But you only can vary one thing. That's why it says vary, feed mixed water and stuff, salt out. Input, output. And that's really all we've learned so far in class, other than he's used this binary TXY thing up here. But it's the same system as the solubility. And that's all we've done, and that's the homework with extra stuff. Now you know, if you were to theoretically set up some sort of dissolving system, you could have this nice feature here to let you know.
Well, thanks so much. I appreciate it.
Oh, no worries. Right, I'm going to stop sharing, and then I'm going to stop recording.